regulated variable, generally it's a pressure that goes to a valve, and that changes something in the system. That changes something in the system which determines a new control variable. Or I could have, and I could also have external disturbances to the system that also contribute to the value of the control variable. But the whole point of control is to compare the control value of the control variable that I can measure to the set point. And if there's a difference, to try to use the controller to correct it. If I had no controller, then I wouldn't be manipulating anything, and this would be cut off. I would actually just be cut off here. I just have the process moving along, giving me that CV prime, and maybe some with some disturbances coming in, which would just give me CV prime. I would just have this little region here, and CV would be doing whatever it felt like, which is generally not what we want. So we started talking about what type of controller we would like. And we would like the so-called, the controller we're going to talk about is the so-called PID, proportional integral derivative controller. And we spoke about all sorts of reasons why we like the PID controller last time. And so rather than repeating that, I'm just going to review a little bit what we did last time, especially since there was this long weekend this week. And it's going to be an even longer weekend next time, not in duration, but in people's activities. And we noted that we could write CV prime tilde in terms of the disturbance D prime tilde and the set point, because typically what is affecting my system? What's affecting my system is there are disturbances that affect my system, and I could have many kinds of disturbances. So they can affect the system, but I can also affect the system by changing the set point, by something that I choose. That is, the system could have been moving along nicely, but all of a sudden the customer said, I don't want 90% purity, I want 95% purity. I'm not going to pay for 90% purity. So all of a sudden the set point changed, often due to the customer. So we also want to know what happens. We want our controller to know what to do when the set point changes. That's all built into the control algorithm. So here we found how CV prime reacts to D prime tilde and SP prime tilde. Disturbance and a change in the set point. And we found transfer functions for both the response to the disturbance and the response to the set point change. And from this general formula, which we leave up there, we wanted to try it out with some examples. So one example was 3 CSTRs in series, where I worked out in great detail in the last class what the response to the disturbance is. So here the disturbance was in XAB. So if you remember, it's a little bit cramped up there because the original picture was erased. But what we had here was we had 3 CSTRs in series. And what was going on is we had A reacting away to products, where A was the reactor. And what we had here was 2 types of inlets. We had an inlet, the normal inlet, which had a large volumetric flow rate and a low XAB. And we call that the flow stream B, and little b. And the concentrate, or the mole fraction of A in stream B was not too high. It was typically coming from another part of the plant, but it had a large volumetric flow rate. And what we did is when it went through the 3 CSTRs, we would analyze what came out of the 3rd CSTR. And if we didn't like it, if it wasn't what we wanted, if there was an error when we compared it to the set point, then it would send a signal to open a valve here, where this valve had a reservoir of very high concentration A, big A, but generally the flow rate would be either 0 or very small, because even a little bit of this would change the effective XA coming into the reactor. So that was the system that we analyzed in great detail. And we found that the effective XAB, a disturbance to XAB, could be written as K disturbance over 1 plus ST, where T was the time constant of the system. And that Q, and it was Q because I had 3 CSTRs in series. We also found what the GP was. That is, when I change VA a little bit, the response to VA, that is, I increase the flow here of the high concentration stream, it's a small flow, then we calculated its effect on what comes out, GP, as the steady state gain divided by 1 plus ST cubed. And that's no surprise because both XAV and VA go through all three reactors. That's why I have a 1 plus ST cubed. And also because we know that the T, the time constant, doesn't depend on the actual disturbance. We saw it's a system property. It's not a disturbance property. So they both have a 1 over ST cubed, they just have a different K in the numerator. This is the steady state gain for the change in VA, and this was the steady state gain for the change in XAB. And then we had KV, KC, and KS. What we assumed that was the sensor was true, so that there was no effect, no time-dependent effect of the sensor, so we just assumed that KS was 1. KV was the valve, and we saw that the valve, we said that GV was just, which was the volumetric flow rate coming out when I open the valve or close the valve, divided by the pressure coming in, which or if you like, divided by the position of the valve, that we could just assume that was linear, so it was just alpha KV was GV. And then depending on what KC was, we got different results. Depending on what the controller algorithm was, we could see what would happen. So what did we do? We decided, say, well, let's assume that I only have the disturbance, no change in the set point. So I only look at this guy. And let's assume I have proportional only control. That is, I manipulate the manipulated variable just in proportion to the error. So if the error it doubles, I double the manipulated variable. If the error is in half, I half the manipulated variable. And when we plug that in, we plugged it in here, and we saw we had this quantity here, and we noted that we could take use the final value theorem. And the final value theorem said, well, let's solve for CV prime. CV prime is G times D prime tilde. So it's G times D prime tilde. And limit of CV prime as t goes to infinity is limit as s goes to 0 of s CV prime tilde, which is s G D prime tilde. So when I did that, D prime tilde as a step, if this is a step change, gives me delta D over S. When I multiply by S, the S's cancel. Here I have D prime tilde. And notice when I take S goes to 0, I got something that was not 0. So that told me that proportional control in and of itself has a problem in that the limit is CV prime of t as t goes to infinity is not 0. That is, there's a disturbance that enters the system, and the control variable with this control algorithm does not return to the set point with proportional control. So that says I don't trust proportional control on its own. And we spoke about that. What we said on that was, proportional control. How is that possible that I have a proportional control? I have this control algorithm, which seems pretty logical. The worse the error, the bigger the control action. That sounds pretty reasonable. How is it possible that when I rely on proportional control, things don't work out? That is, I get an offset. Well, if we think about it a little bit more subtly, what we find is before there was a disturbance, the manipulated variable had a certain value. And with proportional control, the change in the manipulated variable is proportional to the error. It's proportional to the error. Well, if I return to 0 error, if this really would work, to 0 error, would say that the manipulated variable would return to where it was before there was a disturbance. Before there was a disturbance, when there was no change in the manipulated variable, I was at steady state. Now I've added a disturbance. How can it still be at steady state? I've added a disturbance, and the manipulated variable hasn't changed. So when you think about it that way, it's obvious that proportional control can't do the job on its own. Because I had something in steady state with no disturbance. I introduced the disturbance, and if it were at steady state, the controller would do nothing. How can I introduce a disturbance, the controller's doing nothing, and the thing still stays at steady state? Can't be. So that's a problem with proportional control. Let's think a little bit more about proportional control before I go on and set up one other example that we're going to use, and then we talk about other types of control. Let's look at what's going on here. Notice that CV prime tilde. So here I wrote, this is the final value theorem. But remember, this quantity here, before I canceled the S, was CV prime tilde. So let's just note, and maybe I'll just rewrite that over here. CV prime tilde was equal to, well, let's just copy it there. It's KV divided by alpha KP KV KC plus 1 plus ST cubed, which I'll write that out in 1 second, times delta D over S. And let's write out 1 plus ST cubed. 1 plus ST cubed is 1 plus 3, so I'm going to multiply it cubic. So here I'm going to have S cubed T cubed. And if you multiply it out, you'll see that what you get here is 3 ST squared plus 3 S squared T. And here I have, that's what the denominator looks like when I multiply it out. And this is CV prime tilde. Well, let's notice something. Here I have a cubic in the denominator. So I've got S cubed times something, S squared times something, S times something plus a constant. So this is the constant. Now, a cubic, and notice all of the coefficients are real because T is positive. So if all the coefficients are real, how many roots does a cubic have? 3. A cubic has 3 roots. Now, at least one of those roots has to be real because all the coefficients are real. Yep.
Isn't it 3ab squared plus 3a squared b? Shouldn't it be s squared t squared plus 3st?
3st squared plus 3s squared t. Oh, did I lose? No, I didn't lose anything. What's the problem?
I thought it should be 3s squared t squared plus 3s.
No, s squared t squared. No, just multiply it out. You're not gonna get any s squared t squared terms. Or I mean, we could 1 plus 2st plus s squared t squared times 1 plus st. So I get 1 plus 2st plus s squared t squared plus st plus 2s squared t squared plus s cubed t cubed. Okay, so did I do something here? So maybe I lost something. So I've got 1 plus 3st
Plus 3s squared t squared.
plus 3s squared t squared. Okay, thank you. My mistake. Thanks. Okay, my mistake. Okay, so there we have. So let's get back to where we were going there. We're saying that this is a cubic equation. The coefficients are real. So I either have 1 real root or 3 real roots. And remember, it's the denominator that gives me the roots of the zeros of the denominator or what tell me about the stability of the system. So what you can see is, let's say I start out by changing Kc. By changing the strength of the proportional control, I change what the constant in this cubic equation. So I change the roots of the equation. By changing the Kc, I change the roots of the equation, and I could change the stability. So for example, if I start out with Kc really small, if Kc is really tiny, then this thing is tiny, and the denominator looks almost like 1 plus st cubed. So all the s's look pretty close to minus 1 over t. So if Kc is really tiny, then all three roots, s star, look like minus 1 over t, plus a little bit. Because this term becomes tiny, and the solutions just look like 1 plus st about equal to 0, so s is about minus 1 over t. So in that case, all three roots are real and negative. So if all three roots are real and negative, the system is stable and there's no oscillations. What happens as I start increasing Kc? As I start increasing Kc, then the constant starts getting bigger and bigger. And you can imagine as the constant gets bigger and bigger, then not all three roots stay real. Two of the roots become complex conjugates of each other. If two of the roots become complex conjugates of each other, as long as the real parts stay negative, the system will still decay, but it will decay and oscillate. You could imagine if Kc gets big enough, one of the roots, or both of those complex roots, the real part might even become positive. And then the system would oscillate and grow. What's going on there? What is that saying physically? What that's saying physically is, let's look at this notion of proportional control. If we look at this notion of proportional control, what this says, and let's draw a little picture. So let's say here is a step, here is the input, the disturbance. So the disturbance is a function of t. It used to be 0, and when t is equal to 0, I get a step change. I have disturbance. And now I want to look at the output, Cv prime. And I might also look at the manipulated variable. Actually, why don't we look at mv and then Cv? So the manipulated variable wasn't doing anything. mv prime would be 0 until t equals 0, and the control variable was at its steady state value. Now let's look what happens. When Kc is small, then that says the manipulated variable is not doing much. This went up, and the manipulated variable kind of looked like that. It just went down a little bit to take care of that. So as a result, the control variable, which all of a sudden went crazy, now is going to start to decay exponentially. As we said, the roots are real, and I'm going to have a time constant that's roughly minus 1 over t. Well, what happens now? This is Kc small. Now Kc gets bigger. Actually, I don't want to take the whole blackboard, so let's use different colors. Okay, so now we have Kc small, and all three roots are real and negative. Now I go to Kc bigger, medium. One real root, two complex conjugate roots with negative real part. So now in this case, the response is bigger. And instead of CV just decaying exponentially, CV, well, the curve is going to get sharper, right? It's going to start to oscillate. So it may respond faster, but it's going to oscillate and decay. Because now I have complex conjugate roots. Let's look at KC really big. Then now I still have one real root, two complex conjugate roots. But they have now positive real parts. And by the way, here, the manipulated variable is going to have to oscillate to keep up with this. It's going to be out of phase. When this thing goes down, this thing goes up. So this is always trying to fix this. When this goes too low, this goes a little high to override it, etc. Now let's look at this case where it's big. When it's big, this thing just totally overreacts. If it overreacts, then this thing goes down a lot. Well, now this thing has to go up a lot to fix it. And this thing goes up even higher, so this thing goes down even lower. And what happens is it becomes unstable. And this manipulated variable is doing crazy things to kind of try to keep up. So what's happened there? What's happened is I have to be careful with KC, with proportional control. It never quite went to 0 here. It went to an offset. And I should have had this thing going to an offset. But it went to the offset oscillatory. So at first it went to the offset exponentially. It just took a long time because KC was small. When I increase KC, it goes to the offset faster, but it gets there by oscillation. If I increase it too much, the system overreacts. It's sort of like your crazy friend. You come 2 minutes late, and instead of saying, all right, you came 2 minutes late, your crazy friend goes crazy and starts screaming and yelling at you. So you yell back, and all of a sudden you hate each other. So all of a sudden the system becomes unstable. And that's when KC is too big. Are there any questions on that?
Just on the blue, what's the last sentence on the blue?
Two complex conjugate roots with negative real part.
Thank you.
Okay, now I want you to notice that this happened because I was dealing with a cubic equation. Let's see what would happen if I were dealing with a simpler equation, like a linear equation. All sorts of nice things happen when things are linear. Once things get nonlinear, they're not so nice anymore. It's cubic. So this is the typical case. There's a special case of linear. So are there any questions yet before I set up a second example? So we have one example, a reference example here, the 3 CS pairs in series. The other reference example is going to be a linear one, where all sorts of nice things happen. Reference example. So this one is going to be the example we did in chapter 3. So if you remember, we had a CSTR mixer. And we had a heat exchanger here, a coolant. And we had a theta in, we had a theta coming out. We had a VC, velocity, volumetric flow rate of the coolant, V, a volume. And if you remember, we had, when we looked at this example, we said we looked at the temperature of the reactor, and we looked at d theta dt. And for d theta dt, we had a flow. We had theta in minus theta over tau. So here, again, I'm assuming CV is CP. So here, we're given CV is CP. Tau is the volumetric flow rate. The volume over the volumetric flow rate is constant. So that way, I'm saving myself some of the algebra I've taken the rho volume CV and divided it out already. So I've got flow coming in, flow coming out, and then I also have the heat exchanger, and then I have minus UA times, which was a function of VC, depends on VC, times theta minus theta of the coolant. Where here we didn't make that assumption that I need to worry about the inlet and the outlet temperature of the coolant. I'm just going to worry about this inlet temperature of the coolant, just one temperature of the coolant. So I'm going to assume that the flow rate's high enough that the coolant temperature doesn't change. So if you remember, we did this problem earlier in the semester. And we had how UA depended on VC prime. So if we look at a situation where there could be a disturbance, the theta in can be disturbed. Disturbance. And VC might be the thing that we manipulate. MV might be our manipulated variable. So if we don't like the temperature here, we can measure the temperature, then we can manipulate VC. So that's the part I'm adding to what we had before. Beforehand, we just said, let's look at the result, at what happens as a result of a change in this or a change in VC. So let's just notice what's linear and what's nonlinear. So what's changing? Theta's changing, theta in can change, V can change, VC can change, and theta can change. I'm assuming that the coolant can't change. Yep.
Just to make sure I understand the control variable is volume.
Can you pull your
Just to make sure I understand the control variable is volume.
control? What was the last word you said?
Control variable is volume.
No. The control variable is the temperature at the outlet. So what we're interested in this case is we're interested in controlling the temperature of the outlet. So I have a certain temperature of the inlet, and I also have a coolant stream. So you can imagine the inlet is hot, and I want to make sure that what comes out is not too hot because I want to dump it in the river. I don't want to, but my boss wants to dump it in the river. I would never dump anything in the river, and we don't want to kill all the fish. Unless, of course, they're nasty fish that are invasive species that are killing all the local fish. Any other questions? Okay, because, of course, we want to be nice to the fish. Okay, so you're all with me? All right, so what did we do here? Well, this term depends on VC, so this is nonlinear. So this term is because it's a product, this was nonlinear. So I needed to linearize it, and I wrote d theta dt is equal to theta in minus theta over tau minus. So here I had UA steady state times theta minus theta c. Steady state plus UA steady state times, so this was steady state and this was steady state. Well, theta c never changed. Times theta minus theta c. Plus UA, plus theta steady minus theta c times dUA dVC steady state times VC prime. And this is theta prime. Okay, so what did I do here? I noted I have this a nonlinear term. I copied these two terms down. And if you remember, when we do, when we linearize something, we have f of x is f of x0 plus df dx at x0 times x prime plus nonlinear. So in this case, So what happens here? So, and for f of xy is f of x0, y0 plus df dx at x0, y0 times x prime plus df y at x0, y0 times y plus nonlinear. So here, x0 is VC and y0, x is VC and y is theta. Those are my two variables. So first I write the steady state value. So this thing I just copied over at steady state. And then I take the derivative with respect to the first variable, with respect to theta, the derivative at steady state, that's this thing, times theta prime minus theta c prime. So I don't actually need this, because this is not changing. And then I need the derivative with respect to the second variable, the derivative with respect to VC, so the derivative of this with respect to VC in steady state, and this just comes along for the ride times VC prime. Okay, so now I take the steady state value. So again, I'm assuming steady state for t less than 0. We've done this already, so I'm just reviewing. So this I have 0 is d theta steady state dt is theta in steady state minus theta steady state over tau minus ua steady state times theta steady state minus theta c. Just this thing in steady state. And now I subtract. So when I subtract, this term cancels this term. And I have d theta prime dt is equal to theta in prime minus theta prime over tau. And then I have plus ua steady state theta prime and this should have been a minus. There was a minus. These should have both been minus. Because I had a minus sign here. I'm going to inherit the minus. Minus. And then I have this thing, which I called, I think I called it alpha or beta. Let's call it alpha here. So then I have minus alpha VC prime. And we went to a big fuss about what this derivative was. I calculated because UA was a constant times VC to the B. I'm not going to fuss about that. Whatever it was before, it still is. I'm just calling it alpha. So now let's bring everything to one side of the equation. So I have d theta prime dt plus 1 over tau plus alpha theta prime is equal to theta in prime over tau. So I move this guy and this guy to the other side of the equation. And here I have plus alpha over tau VC prime. All I did is rewrote this equation where I moved these two guys to the other side of the equation. And I'm going to call this thing 1 over t. So now when I Laplace transform, I have theta prime tilde times, this becomes an s plus 1 over t. S plus 1 over t is 1 plus st over t. Is equal to theta in prime tilde over tau plus alpha over tau VC prime tilde. Or theta prime tilde is equal to theta in prime tilde times t over tau 1 plus st plus, let's put the theta in prime tilde out here, plus VC prime tilde times alpha over tau t over 1 plus st. And let's just notice something. The first thing to notice is, okay, so let's look at G tilde for theta in prime to theta prime. This thing is equal to t over tau over 1 plus st. And G tilde for VC prime tilde to theta prime tilde is equal to t over tau times alpha So this is how a change in the inlet temperature affects the outlet temperature. And this is how a change in the flow rate of the coolant affects the outlet temperature. Again, if you're busy copying down what I'm writing on the blackboard, you're training to be a secretary. You're going to have a picture of this and a video of this. You can write down things I say, but don't copy what's on the blackboard. It's more important to listen. Okay, so the first thing to notice is this thing I can usually call a K for the in, or what I'm calling KP. And this thing is the K for VC. So this can be K in, and this can be KVC. But the important thing is, the actual function of S in the denominator here depends on the system. It doesn't depend on what's changing. I've said this a million times. The time constant, capital T, and in fact this form here, all comes from the left side of this equation. The left side of the equation. The left side equation doesn't have the disturbances on it. So the denominator of both of these, come from the left side of the equation, which has no disturbances. It doesn't have theta in prime, it doesn't have VC prime. So that's why it's the same. It's the same for both of them. But I just have different things in the numerator because here I have the alpha, here I didn't. Okay, so that's the reference situation. And now let's go back and examine proportional control to see how it works for first order system. And the point I tried to make before is the first order system is like the A+ student. It always does everything perfectly, but it's not the usual student. First order system is the exception, it's not the rule. The rule are the nonlinear systems. Okay, so let's look, in this case, the way I've set it up, the disturbance is theta in. So this one I'm going to call GD. And this one, because it's the response of the system to the variable that I'm controlling, to the manipulated variable, I'm going to call this one GP. Or if you like, I'll call it GP times GV. Okay, and let's see what proportional control says. Control for first order example. And this is 1, 2. So I have that CV prime tilde is equal to. Well, we know from here, CV prime, it's GD. GD we just said is, let's call it KB, divided by 1 plus ST. Divided by 1 plus GPGV. GPGV is, I'm going to call KP, so I'll call this thing KP. And this thing I'll call KD. KP over 1 plus ST times, okay, I'm assuming GS is 1, but I have the controller, which gives me KC. And I'm assuming that GS is assumed to be 1. So notice, in this particular example, I have a 1 plus ST to the first power in KD and KP, whereas in this case, I have 1 plus ST cubed in KD and KP. It's the only difference. Here with the cube, there was first order. So let's see what happens here. Now, when I multiply this out, well, first let's do the final value theorem. Am I going to do any better here in the final value theorem? So the limit as t goes to infinity of CV prime of t, this limit as s goes to 0, of s times CV prime tilde, which is the limit as s goes to 0 of s times g tilde, this is CV times d prime tilde. I lost that. So it's g times d prime tilde. So that's the limit as s goes to 0 of s times this thing, kd 1 plus st over 1 plus kp kc divided by 1 plus st. That's this thing times d prime tilde. D prime tilde is delta d over s for a step change. Is that clear what I'm doing? So now this s cancels this s. And if I take the limit as s goes to 0, let's multiply through by, if I take the limit as s goes to 0, this just becomes 1 in the denominator, 1 here. And here I get kd delta d over 1 plus kp kc. In other words, CV prime does not go to 0, not equal to 0. And in fact, that looks just like what I had over here. Except, I had all this other contribution of alpha and kv. Kv I've incorporated and alpha I've incorporated. So again, I get the same offset. Offset not 0. Bad. But let's look at the dynamics. The dynamics in the cubic system, we saw could go through this metamorphosis through here because I have the roots of a cubic. When I have a linear equation, I'm not going to get complex solutions to a linear equation. I get complex solutions to a cubic. So let's look at this. I have CV prime tilde is equal to, let's multiply through by 1 plus st. So I've got kd divided by 1 plus st, well, 1 plus st, I multiply top and bottom, plus kp kc. Okay, well, let's divide top and bottom by 1 plus kp kc. This is kd over 1 plus kp kc. Divided by 1 plus s times t over 1 plus kp kc. So notice, this looks like a constant divided by a linear term. And that's something we can invert. We can look at that in gory detail. So this is our chart, and this is the one you have. And this looks like, and of course I lost the one, a 1 over s. So I've got a delta d over s. So I've got a delta d, and I've got a 1 over s. So we need 1 over s, 1 plus s tau. So this is line 5. And this tells me that CV of t is equal to, all these come along for the ride, kd delta d 1 plus kp kc. Constants come along for the ride. And this just becomes 1 minus e to the minus t divided by t over 1 plus kp kc. Just from line 5. We've done that inversion many times. And let's see what happens. And this is with control. No control, when we're out of control, CV of t, CV prime of t. With no control, if there's no control, then kc is 0. So that would just say kc is 0. So I get the same thing with kc is 0. I have kd delta d times 1 minus e to the minus t over big T. And let's compare control and no control. No control means the manipulated variable is 0 times the error. No control. I don't do any control. So notice both of these have exponential decays. However, let's notice that in this case, there is a time constant big T. And big T, we said, depends on the system. It all came from the left side of the equation. It came here, it was 1 over tau plus alpha. It was just from the system. So I would get an exponential decay. Here I also get exponential decay with proportional control. But notice the time constant here, the time it takes for the curve to decay. Here it's t, and here it's t over 1 plus something. So the bigger Kc, the smaller the time constant. So instead of decaying like this, it decays faster as Kc goes up. So as Kc goes up, it decays faster, and what it decays to gets smaller. So in this case, as Kc goes up, the offset goes down, and the time it takes to get there also goes down. So this is the superstellar student, the first order system. For proportional control, the higher Kc, the bigger the gain, the better. The lower the offset, it never goes to 0, and the faster you get there. But you see, that's pathological, that's for a first order system only. The minute you get nonlinear, you have to be very careful. You start cranking up the gain from a little reaction to a medium reaction to an overreaction, you can introduce oscillations and you can make the system unstable. You can't do that in a first order system. Any questions on that? Okay, spent a lot of time on that, but I think it was worth it. So, questions? So what do I do about this offset? I don't like offsets. I don't like it, nobody likes it. If your controller, first with proportional only control, you never get rid of the offset. And then if you try to crank up the proportional controller, you blow the system up. Both of those are bad. So I need to augment that. And to augment that, or use a different controller. So we're going to introduce integral control. And for integral control, we say that mv prime of t is going to be equal to kc times an integral from 0 to t e of t prime dt prime. Well, let's see. Beforehand, for proportional control, I had a k for the controller times an error. So k for the controller had units of the manipulated variable over the error. I would like to keep kc having the same units. So I noted that this is not the error, but it's the error, the units have an extra time in it. So I'm going to divide through by some sort of time constant for the integral control. And that way kc will have the same units it had before, where kc is the k for the controller. It's going to be the gain, and it has those units. And then, of course, I have some initialization, I. So this is mv, and of course, mv steady state is going to be kc over ti. Well, at steady state, this is for t less than 0. I have the integral from 0 to 0, which means this thing is just going to be 0 plus I. It's the integral from 0 to 0 is 0. I subtract, and I get mv prime of t is equal to kc over ti, integral from 0 to t, e of t prime dt prime. So this I is just put in so that at steady state, the manipulated variable is fixed, just as it was in the proportional control. Now let's take the Laplace transform. mv prime tilde is equal to kc over ti. Okay, who remembers what the Laplace transform of an integral is? What's the Laplace transform of an integral? 1 of res times e. So it's e prime tilde divided by s. So therefore, g for the integral controller, gc, is equal to mv prime tilde, I'm sorry, it's e prime, mv prime tilde divided by e tilde, e prime. And that's equal to kc over sti. And now I can go back and look at the two examples I've looked at until now. So let's look at the first order example and the third order example. So for the first order example, the only thing that's going to change is Kc is now, instead of just going to be Kc, I'm going to have a 1 over STI in there as well. So for integral control, this is now going to have an STI, integral control. So if that has an STI, then when I multiply through, because I want to save myself some writing here, CV prime. I'm looking at CV prime. So it's the exact same thing, except I have to multiply top and bottom by STI. So I have the exact same thing here, but I multiply top and bottom by STI, not just by 1 plus ST. So that tells me that CV prime tilde for the first order example is equal to, it's equal to this guy, KD delta D over S times 1 plus KP KC plus ST. That's exactly what I had before without this. And now I multiply top and bottom by STI. So I've got an STI and an STI. And that's the case for integral control. Only integral control. Purely integral control. So I can make these blue if you like them. Prefer that. And let's see what happens there. Let's look at the final value theorem. The final value theorem says that the limit as t goes to infinity of CV prime of t is the limit as s goes to 0 of delta d over s times s times, and of course I left out the delta d. No, I didn't leave it out. There it is. It's delta d. So what do I have here? I've got the delta d, I've got kd, I've got STI divided by STI times 1 plus KPKC plus ST. Is it clear how I got that? I took this thing, which is CV prime tilde, I multiplied by S, so I multiplied by S, and I'm going to take the limit as S goes to 0 to see what CV prime of t is. Let's take the limit, let's cancel S's. I cancel S's. And, except I don't need this STI here. So let's go back a step. When I do too many steps of algebra at the same time, I make mistakes. So if you remember, I multiplied top and bottom by 1 plus ST to get this. Now I have an STI down here. When I have an STI down here, I multiply the top by STI, that's what I got. And when I multiply the bottom by STI, this thing cancels here, but the 1 turns into an STI. So I have to be a little careful when I multiply through by STI, and I should be even a little more careful. Let's just, maybe I'll do all the steps instead of trying to get away without doing all the steps. Okay, so when I multiplied by 1 plus ST, I got this. So let's write that. So I've got KD delta D over S 1 plus KP KC plus ST. That's what I got when I multiplied by 1 plus ST. But now I need to multiply by STI. Well, when I multiply the numerator by STI, I get an STI. And when I multiply the denominator by STI, the 1 plus ST gets an STI times it. So the 1 plus ST, so I have the KPKC. And then I have a 1 plus ST, which came from here, that gets multiplied by STI. So when I do that carefully, which I should have done before, the 1 plus st times sti multiplies this. 1 plus st times sti multiplies the 1. The kp plus kc stays. The 1 over s stays. And here the 1 over st cancels and I get an sti in the numerator. So this time I think I actually did the algebra correctly by doing it twice. STI, STI. And let's see what I get here. So let's do this, rewrite this correctly. I've got KD delta D STI. And in the denominator, I've got S, as we said, KP, KC, plus 1 plus ST times STI. Okay, so now, and this STI came from the integral control. Okay, now let's take the limit as s goes to 0. If I take the limit as s goes to 0, notice in the denominator this becomes 0, this becomes 0, but I still have a positive quantity kp, kc. So as long as I have control, I have a positive number here, but the numerator has an extra s. So I have 0 over a positive number, which is just 0. So what happens is there's no offset. Now, what we saw is that in proportional control, I had an offset for the 3 CSTRs in series, and for the first order system, I also had an offset. Where did it go? Proportional control, offset, bad. Here, as soon as I put integral control in, there's no more offset. Well, that sounds great. So why don't we just use integral control? Well, let's think for a second. Integral control depends on this integral. At small values of time, even if the error is big, it's multiplied by, it's integrated over a small region. So even if the error is big, the integral of the error over a short time is very small. So that says the controller is going to be very sluggish. Even if I have a big error, the integral of a big error over a small time is still small. So this is going to be very sluggish. In other words, the controller won't start to react until the integral becomes big. So even though the integral gets rid of the offset, it'll take a long time to do it. So I don't want to just have integral control. Maybe I want to combine integral and proportional. Proportional acts quickly, but doesn't get rid of the offset. Integral gets rid of the offset. And you can notice, at long times, integral control is good. Let's say my error looks something like this. If my error looked something like this, the proportional control, the controller would always be doing the same thing because the error would stay constant. So the manipulated variable would stay constant, and I'll never get rid of the error. On the other hand, if I integrate this, I get something that increases with time. And as time goes up, the integral of the error gets bigger and bigger, so the manipulated variable responds more and more. So when I have to combine the two of them, I can get relatively fast response, but at long times, I don't tolerate an offset. In other words, with proportional control, at long times, I still have this offset. And if the offset is small, the proportional controller doesn't care much. But the integral controller hates it, because when I integrate this, when I integrate a small offset, when I integrate that, the integral of the offset grows. The integral keeps going, gets bigger and bigger, whereas the offset would stay the same. So this tells me the controller is just going to keep reacting more and more until it gets rid of that offset. Is there a hand up? Well, okay, why don't we look at the 3 tanks case? Let me just see if there's anything else I want to say there. Yeah. Okay, let's look at the 3 tanks case. In the 3 tanks example, again, here it is, except now I'm going to do all the algebra. So I've got GD, D, and that's equal to KP over 1 plus ST cubed, divided by 1 plus, and this was KB, KP over 1 plus ST cubed, alpha times KV. He said that's where I got the alpha. I've got the 1, and now this is KC over STI. So the only difference is instead of this just being KC, it's KC over STI. So what happens there? Now when I multiply by 1 plus ST cubed, I get KD. I'm not just going to multiply by 1 plus ST cubed, I'm going to multiply by STI as well. So that cancels and I get an STI. And here I get 1 plus ST cubed times STI plus KPKC. And here, that's what happens when I multiply by 1 plus ST cubed STI in numerator and denominator. Notice this looks just like this thing when I finally did it correctly. Looks just like this when I finally did it correctly. Well, here it is. So here this was 1 plus ST, here it's 1 plus ST cubed times STI plus KPKC. So it's exactly the same. And now when I look at CV prime, the limit as t goes to infinity of t, this is the limit as s goes to 0 of s GD times d prime tilde. The limit as s goes to 0, s delta d over s times kd STI over 1 plus ST cubed STI plus KPKC. And now again, these s's cancel, and the denominator, when s is 0, this term drops out, but I still have a KPKC. So I have a number in the denominator, and I have an s in the numerator, so this thing goes to 0. So in this case as well, it gets rid of the offset. So the integral control gets rid of the offset, but it's sluggish, it's slow. So it would be great to combine the integral and the proportional. Are there any questions on that? Now, let's just note that in this case, with the integral, well, first of all, why is the integral controller doing such a good job on the offset? Because when I have an STI in the denominator, then when I didn't have the STI in the denominator, when the STI wasn't in the denominator, then when the STI wasn't in the denominator, then notice I had, well, where is it? Let's look at the case when I did. Let's see. Yeah, up here. Thank you. When I didn't have the STI in the denominator, then when I multiply through by 1 plus ST, I had the 1 plus ST here plus a constant. I had a constant here. And when I multiplied by delta D over S times S, I just was left with the delta D. So I had no extra S's in the numerator. All the S's were gone from the numerator, so the constant in the denominator survived. By having the 1 over ST, when I multiply out, I get an extra S in the numerator. That extra S in the numerator is what gets everything going to 0. If I didn't have that S from the denominator, then this wouldn't be here, and I would have a non-zero, and I would have an offset. So by having the S in the denominator, That's exactly what gives me the, when I multiply through, that gives me the extra s in the numerator that gives me the final value theorem having to go to 0. Are there any questions on that? Yeah? This alpha came from here. If you remember, that was, maybe I shouldn't use the same notation. This alpha, let me call it alpha prime. Alpha prime. That was from the valve. That was GV for the valve from last time. It has nothing to do with the alpha in this case. Now let's just notice, when I look at the dynamics, so I'm looking at CV prime of t, not the limit. CV prime of t is CV prime, well, tilde of s. That's equal to delta d over s, kd, sti, over kp, ac, plus sti, 1 plus st, q. So let's see what happens here. If I look at the dynamics, not just the limit. Remember, when I had proportional control, I had a cubic in the denominator. Now, with integral control, I no longer have I have a cubic, but it's a quartic. It's a quartic equation, not a cubic. So I have 4 roots instead of 3 roots. So now it's possible that I could have 4 real roots, 2 real, 2 complex, or all 4 complex. They're all possibilities. 2 sets of complex conjugates. And the actual value of those roots depends on the coefficients of the quartic. And notice that this part of the quartic involves ti. So ti is going to affect the coefficient of the 4th order, the 3rd order, and the 2nd order. And kc is going to affect the coefficient of the constant term. So both kc and ti are going to affect the roots of the quartic, and therefore they're going to affect the dynamics. And you could imagine that just as things went crazy here in proportional control, things can also be crazy here. That is, when the controller is too aggressive. Again, you could start out by looking at a situation where kc is 0. When kc is 0, then we know what the roots are. You set this equal to 0, and the roots, 3 of the roots look like minus 1 over t. They're all real and negative. But as I start, if I make ti too small or kc too big, this relationship here, kc starts growing. If the ratio of kc to ti, it might be easier to just divide top and bottom by ti to see what's going on. So this cancels. So notice this, the 4th, 3rd, and all the power, the coefficients of all the non-zero powers of s don't depend on the controller, but the constant depends on the controller. So it depends on kc over ti. So if kc over ti is 0, then the roots are 0 and minus 1 over t. I've got 3 of them. So I just get real negative roots, exponential decay. As kc over ti gets bigger, I'm going to get exactly this problem here. That is, I'm changing the roots. They're no longer purely real. Some of them, 2 of them are going to become complex, but they'll start out with negative real parts. And eventually, if I make kc over ti too big, that is, I make kc too big or ti too small, it's that ratio that comes in, because it's the ratio right here, the controller becomes too aggressive, and you get more the roots becoming complex and no longer with negative real parts. So you can have this problem where things blow up. So the controller can't be too aggressive. Are there any questions on that? Okay, so I've spent an awful lot of time on that. Let's get to the final part of the PID control. And have you taken pictures? I only have a few minutes, so we really need to take the pictures quickly.